It is difficult to overestimate the importance of symmetries in shaping the characteristics of matter. Crystalline solids are particularly intriguing because of two opposing extremes. Higher symmetries force emerging degrees of freedom to resemble free particles, leading to the creation of massless Dirac or Weyl fermions that recover practically the entire Lorentz group of free space at low energies. A second strategy is to investigate low-symmetry systems with unique outputs. Among these, chiral or asymmetric systems have a unique role in biology, chemistry, and physics. The absence of mirror, inversion, or roto-inversion symmetry characterizes an object as structurally chiral. An achiral item can be superimposed or is identical to its mirror image. For instance, the ball is achiral since it cannot be recognized from its mirror counterpart. Our hands, however, provide as a good illustration of chirality because they are non-superimposable mirror replicas of one another. Chirality can have unexpected results. For instance, one version of the carbone molecule emits a spearmint smell, but its chiral, mirrored equivalent emits a caraway scent. In the field of material science, one can tell whether a crystal's periodic arrangement of atoms is chiral or not. If it is, then the electrons and electric currents flowing inside of it must also be different in some way from their mirror counterpart, a quality that can result in unusual reactions and unique uses. One illustration is a diode-like effect known as electronic magneto-chiral anisotropy, in which the electric currents running from left to right are different from those going from right to left. This effect has only so far been identified in crystals that are structurally chiral. The Kagome superconductor cesium-vanadium 3 antimony 5, however, is a fundamentally achiral crystal, and an international research team has now reported the first observation of chiral transport in this crystal. This substance is one of the most recent Kagome superconductors with a complex band structure. Vanadium atoms form a two-dimensional Kagome lattice in the crystal structure, which is created by alternately stacking an alkali metal layer and a vanadium antimony layer. The fundamental quantum paradox is this: if the atomic locations in a crystal are identical to those of their mirror image, how can its electrons not be? Evidently, a novel mechanism is operating beyond the simple shape effect we see. This new electronic chirality can be switched using magnetic fields, unlike structural chirality, which is as securely stamped in a crystal. Switchable chirality has never been seen before and could very likely be used in technology in the future. It is obvious that the strong electronic interactions are the cause of this peculiar behavior. Although the atoms are placed symmetrically, the researchers suggest a model in which the electrons arrange themselves in ways that defy mirror symmetry. The investigated compound is already recognized for a variety of these interesting electronic structures, such as the emergence of an unusual chiral charge order with an alluring charge modulation. These chiral electronic structures might rotate on their own, resulting in a magnetic orbital effect called as loop currents. The substance seems to be an incredible laboratory for investigating correlated quantum phenomena, including the first instance of switchable electronic chirality. The next stage is to expand the operational range from cryogenic to room temperature and to increase the response's amplitude. Clearly, interacting systems on geometrically frustrated lattices have much more to offer.